Hello, everyone. It's an absolute pleasure to join you today for this important session on quantum technologies for climate. My name is Raghunath Koduvayur. I'm heading marketing and communications for IQM quantum computers. Previously, I've led business teams at Nokia, Microsoft, Procter& Gamble, and a few startups. IQM is a European leader in building quantum computers. We deliver on-premises quantum computers. I'll cover more about IQM and also how we approach these problems in my second part of the presentation. But let's first move on to the overview of the topic itself. In early 1980s, one of the forefathers of quantum computing, physicist Richard Feynman, said, "Nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." In the context of climate change, let's take the example of emission of carbon dioxide, carbon monoxide into the atmosphere and its reversal through new clean fuels and energy storage. These are functions of nature and must be observed at a quantum level. Quantum computing function in a fundamentally different way from traditional computers. They work more like nature. So hopefully we can use them to understand better how nature works. And then we can also use it to solve the problems that the nature is currently facing using quantum computers. We all know or we have heard that quantum computers are very good at solving certain types of problems, like factorizing numbers, for example. But the focus should not only be on that, but the focus should be on how can we use these quantum technologies for the well-being of humankind. The question that also comes up at times is climate crisis for real? In my opinion, it is. It is an existential threat, not just for us, for our future generations. Reduction of our carbon footprint requires understanding of this science. To tackle this climate crisis, we need to understand nature. The best way to do that is by simulating the climate model and chemical interactions, for which we need powerful computational devices. The devices that we have right now, the supercomputers, are not enough. Similarly, let's take other examples like finding alternate fuels, improving electric vehicles for higher adoption, other discovering new materials. These all require research which need higher computational capability. And this is the promise that quantum computing offers. And there's an urgency. There's an urgency to accelerate these R&D phases so that we can move towards actionable solutions. So, we have also noticed that high performance computing centers are not able to provide that kind of acceleration of computation power that is needed to solve these problems. So we went out and also spoke and discussed with several HPC centers in a research. We connected this research with IDC, Europe, and we discussed with over 110 supercomputing centers or HPC centers globally. 76% of HPC centers said they plan to adopt quantum technologies by 2023. 71% of our total respondents also mentioned that they plan to adopt on-premises quantum computers by 2026. These are big numbers because HPCs are already facing several challenges to meet the current demands and expectations. First and foremost, HPC centers are incredibly energy hungry. For example, some of these machines require up to 100 megawatts of power. And as these machines grow, this kind of energy consumption is not sustainable. Training an artificial intelligence to run an algorithm on a HPC center can produce anywhere between 200K to 300K carbon dioxide in its life cycle. We need to find an alternative to HPC centers. Maybe we need to find the next generation computing technology, which is where quantum comes in, quantum computers comes in, which are much more powerful and which require significantly lower energy for consumption. Let's move forward and see why they are so less energy consumption, like why they consume so less energy, and also how can we use them to solve the problems that we face today. So what is quantum computing? Quantum computing, like unlike, let's start with the classical computing. Classical computing is programming based on zeros and ones. But we know that things are not that simple in nature. It's never binary. Everything moves on a scale. And that's how quantum works. So they exist in both 0 and 1 at the same time. In quantum computing and quantum technology, the computers replicate nature and they are not binary. And this enables us to replicate or reproduce the things that we see in nature also on computing devices that require less energy. And also because quantum computers employ distributed amplitudes rather than work through a sequential yes or no decisions. They have potential to solve problems that are far beyond the reach of today's machines. So when to use quantum? This is a very simplified version of when a quantum computer will be used. And this is also a good point to just reinforce the message that quantum computers are not going to replace HPC centers. Quantum computers are not going to replace supercomputing centers. But at least I personally think that these two will coexist in a way where quantum computers, which they are exceptionally good at solving certain kind of problems, will be addressing that part of the problem, and then it will be passing on that problem or that solution to a HPC center, which will dig deeper into their expertise and then try to find the answers that we need. So these two will work in a tag team where a quantum computers will coexist with a HPC or a supercomputer. This is one of the examples, like hybrid variational algorithm, where you can see how a quantum computer and a HPC will coexist. But the thing with over promising about quantum is also the risk that we will too soon start becoming impatient. So let's focus on what is actually possible and what are the timelines that we are working with. And this is very important because quantum computers at this point still have several hardware challenges. They are still in early stages of development. So likely that they will not be able to solve most of the problems that we have. But BCG has put up this great visual representation where even in the NISQ era of quantum computers, which are the areas that we can focus on? Because the world needs to find ways to take collective action now. And this also does not prevent us from looking at alternatives like through the current computing methods, but we should also start looking at alternatives in the way of quantum computers, which could represent or which could bring in a solution which the world does not have right now. For example, if applied to current low emission technologies, quantum computing could contribute to solutions that change how we generate and store power, how we build houses, cars, ships, aeroplanes, how do we power transportation, and even how do we design long-standing industrial processes such as cement, steel, fertilizer, the list goes on. Let's take a few examples. Green hydrogen power. Accelerating this kind of a development of new catalysts which can split water molecules replaces quite expensive platinum and increasing the efficiency of current conversion processes. This could significantly decrease the production costs for green hydrogen, which means green hydrogen can displace methane steam processes. Even more important, it could put low carbon hydrogen within economic reach as an energy source for transportation as well as steel production. Carbon capture is another good example. Better catalysts could significantly increase efficiency and lower the cost of binding carbon. But let's look at two specific examples and maybe dig deeper on where does the quantum computing play a role and why is it able to solve certain problems better. This use case is an important one, ammonia. We all know ammonia as one of the best known fertilizers, which could also be used as fuel, potentially making it one of the best decarbonized solution for ships. There is a current process which is the Haber-Bosch process for producing ammonia fertilizer, and it consumes, depending on which study and how you see it, at least 3 to 5% of all the natural gas generated globally. So ammonia consumes about 3 to 5% of natural gas which is generated globally. And it has not changed because this was invented a century ago and the process still continues. What if we are able to understand how bacteria produces ammonia naturally, using significantly less energy and replicating the molecules within ammonia? This would be a big step forward. A new green product, for example, which will be cheaper ammonia, will not only bring down emissions in the CO2 intensive processes worldwide, but it will also give us an alternate fuel. There are also other approaches, which you can see on this graph here. A nitrogenous bioelectrocatalysis, which is how nitrogen fixation works naturally when plants leak nitrogen gas directly from the air. These enzymes catalyze and convert into ammonia. So this method is done at very, very high temperatures. But with this new approach, we should be able to bring it down from, say, 500 degrees centigrade to a room temperature, which means production of ammonia will also be energy efficient. Using quantum computing to facilitate cheaper green ammonia can also be used as a shipping fuel, which will again reduce the carbon dioxide emission, which I will show also in one of the last slides, where if we sum up all of these efficiencies and if we facilitate all of these kind of new innovations, how much impact it will have on the climate crisis. The second example I have is from the future of data centers. Data centers, we all are consuming data every second of the day. Now the video that you're seeing is also consuming data and a data center source. And there are many challenges that data centers face right now, right from computational limitations to expensive, like it's becoming quite expensive to run these data centers. And the third one is also on the energy, so energy consumption. So there are many such challenges that data centers face. A classical computer, if you look at it as supercomputer, can spend about maybe say $70 to $80,000 to solve a specific problem around, let's say, maybe AI. A similar problem, if you compare, there have been studies that have been done where a quantum computer can do it for less than $1 or $2. So about 70 to 80K dollars to $1 with quantum. Why is it possible? It's not just because of that quantum computers are are fast, but it's also because they consume significantly less energy. Even if you take the same time that both HPC center and a supercomputer and a quantum computer run for the same time, you'll notice that quantum computers consume significantly less energy. And this is because of various reasons. Like a quantum computer works in a cryostat, which is already super cool, and it's trying to solve problems much faster, exponentially. The other thing also we need to consider is how a supercomputer is built and how a quantum computer is built. A supercomputer has thousands of CPUs, thousands of GPUs, and also thousands of classical control equipment like components, while a quantum computer has maybe about hundreds of equipment because it has a large cryostat, a quantum processor, some cabling, and some electronics. So there is significantly less energy consumed, both in terms of running a quantum computer but also in making a quantum computer. And this will again help us in solving one of the biggest challenges, which is the energy consumption by data centers. And here you can see in this graph how quantum and a HPC center will coexist. As I raised in one of the slides earlier, that I don't expect quantum computers to replace the HPC centers, right? Nobody does. Now, industry experts say that these two will coexist. But it will coexist in a way that it will be like a tag team where both the computational devices will be talking to each other and will be playing on the strengths to jointly solve a problem. And that is the way I see and we all foresee how a HPC and a quantum will coexist. Now the question can come up, why now? Because until now, even with Moore's law, we've been able to keep pace with the computational demands that we have had. But now we foresee that it's no longer possible to keep pace with the demand for data related technologies and also computational power that is needed. Prices are going up and it's becoming very expensive to run these data centers and also maintain these systems. And the third one is the energy consumption. So it makes it a perfect timing now when even the quantum technology is slightly improved. The hardware has developed to an extent that we can try to run the early stage algorithms. And for maybe some problems, we will reach quantum advantage in the short to medium term. So this is a good time to start working on quantum readiness and start building on this capability across the world. So now let me dig deeper into IQM. IQM is a European leader in building quantum computers. We deliver on-premises quantum computers. We've already delivered one in Finland to Finland's research center VTT as part of a co-innovation project. And we are also building one in Germany now with the LRZ, which is the third largest supercomputing center in Germany, where we will have a quantum computer which will work as a quantum accelerator together with the supercomputing center. We have 4 offices in Madrid, Paris, Finland, and Germany. And we also have over 190 employees, which is one of the largest quantum engineering teams out there. Our strategy is built on 3 pillars. The first pillar, where we are right now in the NISQ era, is to deliver on-premises quantum computers. We have realized and we have identified that quantum technologies development, not just quantum computing, but overall quantum technologies, quantum sensors, quantum communication, quantum encryption, it requires access to quantum hardware. So we deliver on-premises quantum computers, and this is the first pillar of our strategy. The second pillar is to work with industrial partners on specific problems. For example, a climate crisis is one of those problems. The second one could be battery optimization and new material discovery could be another one. The third one is healthcare. So we are identifying those areas for co-design where we develop chips or quantum processors for a specific problem. The third pillar is where we see universal quantum advantage, where a general purpose quantum machine will be able to solve any problem that we put together. So these are the 3 pillars on which IQM strategy is built, where we see the first and second pillar already trying to address some of the challenges that we discussed earlier in terms of the climate crisis. There are also certain areas that we have identified, in which includes quantum simulation, quantum optimization, quantum machine learning, and also problems that we face in terms of PDE. So these are things that we are looking at. Some of the non-exhaustive methods or work lines that we are working at IQM are these 4 partial differential equations, quantum machine learning, quantum simulation, and quantum optimization. If you ask me where would I personally expect quantum advantage to appear sooner, one would be with the co-design approach, where we work with an industrial partner and then we build a quantum processor for a specific problem. The second one would be, in my opinion, could be the quantum simulation, where we can create algorithms to describe problems that are quantum in nature. This actually goes back to the original idea of Feynman, right? That quantum, nature is quantum, then we should simulate it with a quantum computer. From the applications that we see, we are currently focused on chemistry, quantum chemistry, healthcare, quantum finance, quantum sensing are some of the key areas, and we are also working on certain other areas. It would be useful to determine in detail which climate science application will be the first to benefit this quantum simulation. But that's very difficult to do. But there are approaches that we see, maybe in terms of battery innovation or in terms of chemistry, in terms of new material research. So we do see certain areas which have an advantage, but it's extremely difficult to pinpoint which are the one or two areas which will address any of the climate problems at the first instance. It is also worth noting that when designing a quantum algorithm, you need to look at many other things like the quantum circuit depth and so on. And this is very important because this will also determine how many computational steps are needed to solve a problem. There are, as part of this co-design approach, what we have taken is, what does it exactly mean? Maybe let's go through that. In a co-design approach, if you look at it, if we don't do anything, the horizontal line that you see on the top, if you do not do anything, like no co-design, then that is the number of hardware that you need and the software enablement that you need to reach quantum advantage. So what if we can do a tweak in the hardware requirement, if we can bring the hardware and software requirement lower, and what if we can increase the hardware capability higher? So we accelerate the hardware capabilities that we can build, while also we bring down the need or the demand of the hardware and software requirement. And this is what we are trying. So the generation one will be the co-design gate, where I said we will be creating processes for a specific problem. The second one is where we will try out new topologies. The third one will be, we'll be looking at more elements, computational elements, and then we will also be working on the algorithm part of it, so that we can bring the quantum advantage faster than what has been before. And also on this front, we have done few things already. The first one is we have submitted some papers on the co-design gates. Second, we have also published a NMR paper on co-design quantum simulation. While we are also on the hardware side, we are working on a new qubit type, which is Unimon qubit type. We also have published a recent paper around couplers, and then how the long distance transform couplers enable or reduce an error, and then also the noise. So these are things that we are doing both in the hardware side and also on the software side, while we are also building on our quantum hardware capability. So even if quantum computers, let's just think about it. Quantum computers are not there yet. Why are we discussing it so much now if the climate crisis is today? But I'll challenge it with a different topic. Even if quantum computers can have a slight chance of positive impact on climate change, should we not take it? And this is where I like the recent paper that McKinsey has published, which is fantastic in a way to say, what is the potential of quantum enabled technologies? Can it get the world back on track to net zero? And there, McKinsey has actually listed several areas, which you can see on your screen now, which are very transformative. It is, yes, it takes into consideration that the technology is 5 or 10 years away. But with all the benefits that we can expect and which we can extrapolate at this point in time, there is a significant need for us to pursue this technology, quantum computing. And this is why we also see enterprises are investing in right now. And why is so? The simple answer is, it is a radical technology. It does not build on the classical computing. So if you have classical computing experts, does not mean that they can run quantum computers. Both the quantum programming, quantum tech stack, they all are very different to the classical tech stack and also classical programming. So early adopters will gain expertise, will gain visibility into knowledge, will attract great talent, and we might also address and identify the technology gaps early, which will give them a significant advantage over competition. For example, a drug discovery. So scientists who are trying to work on certain compounds might have a shorter R&D cycle because of quantum expertise when quantum hardware is ready. Same thing in discovery of new materials. So we definitely see that the industry is starting to invest, and invest not just in people, but they're also investing into quantum computing services, and also maybe in some cases also in hardware, because they want to be quantum ready when the technology is ready, so that they'll be able to solve the problems faster. If you leave this decision for later to invest into quantum computing, then they might be left behind as compared to the competition. So the time to act is now, and that's why I'm extremely optimistic about the potential that quantum technologies and quantum computers hold in addressing the climate crisis, if not in the near term, definitely in the medium term, and also for the future. Thank you for having me here, and you can also contact me if you have any questions.